Hello everyone, my name is Andrei Maludin. Together with Sonia Cheng, we are the managing directors of the Beckman Institute Cryo-Electron Microscopy Center here at Caltech. Now, after this presentation, if you're interested in learning more, please find us online at cryo.caltech.edu. Now let's get started. One of the fundamental ideas in biology is that if you have a high-resolution three-dimensional structure of the protein, complex, organelle, or cell, one that can understand its function, as well as any associated diseases. With that information, then therapeutic structures can be developed. On this slide, you can see an animation of translation by bacterial ribosome, and this is possible due to availability of high-resolution structures for most of the complexes involved. As you might be familiar, some of the methods for high-resolution structure determination are X-ray crystallography and nuclear magnetic resonance, or NMR. However, some of these methods have certain challenges that can be overcome with the new addition to the structural biology toolbox, which is cryo-electron microscopy. In cryo-electron microscopy, a sample of interest is purified and a drop of it is applied to a supporting grid, after which we blot most of the sample away and plunge the remainder into liquid ethane maintained at liquid nitrogen temperatures, which is around minus 190 degrees Celsius. This has an effect of preserving your sample of interest in a near native state in a thin layer of vitreous ice. Once the sample is prepared, we put it inside our transmission electron microscopes, which fundamentally operate very similar to light microscopes, except that we trade out the light waves for electrons, and the wavelength of electrons is significantly smaller compared to the photons, so down to about 2 picometers, so our ultimate achievable resolution is significantly improved. Once the sample is inside the microscope, we collect movies, projections, in fact, of our sample, and then computationally we're able to select the particles of interest and get, hopefully, to a very high resolution three-dimensional structure. In around 2012, with the developments and improvements in our detectors, structures to about 3 to 4 angstroms have become routine. In fact, last year, sort of around middle of 2020, resolutions to 1.2 angstroms or atomic resolutions have been reported. In 2017, the Nobel Prize in Chemistry was awarded to Jacques Dubochet, Joachim Frank, and Lucien Henderson for their contribution to the developments in the cryo-electron microscopy. The three modalities of EM at the focus in the center are single particle, where many copies of identical or nearly identical particle can be produced and imaged. From the thousands of images of these particles, then we can get a three-dimensional structure at near atomic resolution. In fact, the highest reported in literature is at 1.15 angstroms. When each object of interest has a unique structure, such as for cells or tissues, then we turn to tomography. In this case, the object of interest is tilted in the electron beam as much as possible, which is plus minus 70 degrees. And from this tilted data, they can get a three-dimensional structure, which is usually in and around 10 angstroms. Now, if there are multiple particles that do have a repeating structure, then we can take some aspects of single particle and average those together and achieve maybe about 3.5 angstroms. And the most recent addition to EM is micro-ED, where similarly to tomography, instead of a tissue, we actually put a crystal on a grid and continuously tilt it as much as possible while collecting diffraction images. And from that, we can also achieve atomic resolution structures. Caltech has been in forefront of cryo-EM, specifically in tomography, through the work that's been ongoing in the lab of Grant Jansen. In 2016, 2 top-of-the-line microscopes were purchased and rolled into what is now Caltech Cryo-EM Center. A new space was remodeled around that time to house the 2 systems. And this new space is shown here. On the right-hand side, we have the sample prep area, and then the central room houses the Titan Krios, and the leftmost room houses the new Thales Arcticon. This is a view inside our sample prep room. In the center we have a Vitrobot which is used to prepare the grids. We can apply our sample through the side ports into a chamber that can be maintained at a specific temperature and humidity. Once applied, excess is blotted off with these pads, and then it's rapidly plunged into liquid ethane maintained in this cup. In this room, we also have a biseptic cabinet to allow for work on BSL-2 material. After the grids are prepared, usually the first stop is on our Thales Arctica. This is a microscope operated at 200 kiloelectron volts and can primarily use for screening, but can also be used for high-resolution collection of single particle data, as well as now microelectron diffraction. It is equipped with K3 direct electron detector and SATA camera for micro LED. If a sample looks good and the inertial structures require slightly higher resolution, then the next step would be the Titan Krios. This is our Titan Krios. The accelerating voltage is set at 300,000 electron volts. As you can see, it is much taller compared to Thales Arctica. And we didn't really see this liquid nitrogen tank on the previous image, but it is also attached to the our microscope. And since our grids need to be maintained at liquid nitrogen temperatures, then the systems are automatically refilled from these tanks. Let's take a look inside the microscope. So at this top door here. So this is the view of the column of a microscope. The electrons originate here at the top, and they're continuing down through the column towards the camera, which we cannot see. In terms of equipment, we have faceplates and bi-quantum energy filter, as well as a K3 direct electron detector. Combined with the high acceleration voltage of the system, this makes it an ideal system for electron tomography, where samples can be a lot thicker compared to single particle samples. On the left-hand side is an autoloader. It is also equipped on our Thales Arctica. This allows us to load 12 grids at a time and then keep them at liquid nitrogen temperatures and exchange them into the column. So both systems effectively are able to run 24/7 with an occasional loading cycle to load on new grids and unload the older grids. Thank you for your time. Hopefully I piqued your interest. If you want to learn more, please visit us at cryo.caltech.edu. See you soon!